Hi guys, today we're going to be learning about prime factorisation. These are our learning objectives. To understand that all composite numbers have prime factors and to factor composite numbers into prime numbers. Okay, first of all, I guess we need to know what prime numbers are. Have a think about it. Can you remember what a prime number is? I'm going to give you a little challenge to see what you've remembered. Pause the video while you write down the first 10 prime numbers. I'll reveal them in a couple of moments. Okay, welcome back guys. I'm going to reveal it now. I hope you've written them down. These are the first 10 prime numbers. 2, 3, 5, 7, 11, 13, 17, 19, 23 and 29. And that list just continues forever and ever as far as we know. Some interesting things to note about prime numbers. Firstly, almost all of them are odd numbers. The only exception is the very first one, 2. So 2 is the only even prime number. 1 is not a prime number, okay, because the definition for a prime number is they have a single pair of factors, 1 and themselves. So 1 is not a prime number because it doesn't have a pair of factors, it only has a single factor. In fact, 1 is a square number. So it's a little bit different from some of the other numbers. So these are the prime numbers because they can only be made by multiplying themselves by 1. They don't break down into any smaller components. Whereas other numbers, composite numbers, are composed or made up from prime numbers. So for example, the number 6 is a composite number because it can be made from the two prime numbers 2 and 3. Because 2 times 3 equals 6. So we say that 2 and 3 are the prime factors of 6. A way to find prime factors is to use a factor tree. I'll show you how this works. So we begin with the number 12 and I'm going to just find a pair of factors of 12 to get me started. You can have a go at this as well on a piece of paper. Write down the number 12 at the top. Let's choose a pair of factors. I'm going to go with 2 times 6. So I'm going to write those factors down and begin to make a little tree diagram. So 2 times 6 is 12. And then I look and see if any of these are prime numbers. And I can see that one of them is. 2 is a prime number. I'm just going to pop a circle around that. And I know that I've reached the end of that branch of the tree there. But 6 is not a prime number. 6 can be broken down further. We've just discovered that 6 can be made of 2 times 3. So I need to continue my tree a little bit further. It has another 2 branches, and 2 and 3 are factors of 6. Both of those are prime numbers. So I'm going to put a circle around them so that I know I've reached the end of that branch of the tree. And now all the branches have come to an end. There are no numbers that can't be broken down further. Sorry, no numbers that can be broken down further. There are 3 prime numbers now at the end of our branch, so we can say that the prime factors of 12 are 2 times 2 times 3. Another way of writing that is to say 2 squared multiplied by 3. Ooh, I don't want that to be up in the air. Okay, 2 squared, because we get 2 times 2 is 2 squared, multiplied by 3. Let's have a look at another example. So this is 32. We're going to find a pair of factors of 32. We can pick any numbers we like that multiply together to make 32, just 2 numbers. So what are you going to choose? Have a think. which numbers would you pick? I'm going to pick 4 and 8, because 4 times 8 is 32. So 4 times 8 is 32. I look and see if either of those are prime numbers. Well, they're both even numbers that aren't 2, so I know that they're not prime. They are composite numbers, which means they can be broken down further into primes. So I need to add more branches to my tree on both sides. Okay, let's see what I can find. Let's work with 4 first of all. I need a pair of numbers that make 4. Well, 2 times 2. It's the only way I could do it other than 1 times 4, and we can't use 1. 1 is not a prime number. We can't end up with 1 at the end, and we'd end up with 4 again, and we'd have to keep going and going forever. Okay, so we're trying to get to a prime number at the end. These are both primes. I'm going to put them in a circle to remind me that I've reached the end of those particular branches. What about 8? Well, 8 can be made from 2 times 4. So let's put that in there like so. 2 is a prime number, so I've reached the end of that branch, but 4 is not. 4 can be broken down even further, so I need to keep going. I need another 2 branches. 4 is 2 times 2. And now I've reached the end of all the branches. These are both prime numbers as well. And this is a really interesting one because actually all of the prime factors of 32 are 2's. So we have 2 times 2 times 2 times 2 times 2. 2 times 2 times 2 times 2 times 2. It's a rather long way of writing the prime factorisation of 32. It's much quicker to write 2 to the 5. 2 to the power 5. Let me just raise it up. It just means 2 multiplied by itself 5 times like this. Okay, one more example, and then I'm going to set you a few problems to try. Let's have a go at 60. So 60, I need a pair of factors for 60. Think about what you would choose. I'm going to go with 6 times 10. That was the first one that sprung to mind. I could have gone for 2 times 30 and I would have had a prime number already, but I've chosen 6 times 10. I'm going to stick with it. So let's break these down further because neither of those numbers is prime. They are both even numbers that are greater than 2, and so we know that they can't be prime. They must be composite numbers. So 6 is a composite number. I can make that from 2 times 3. 2 times 3 is 6. Both 2 and 3 are prime numbers, so I'm popping those in a circle to remind me I've got to the end of those branches. I now need to try and work out what this one's going to be. So 10 is 2 times 5. 2 times 5 makes 10, and both 2 and 5 are prime numbers as well. And they can't be broken down any further. So I've reached the end of this here. Now I could write down 2 times 3 times 2 times 5, but just to make things a little clearer, I'm going to put them in ascending order. So I'm going to do 2 times 2 times 3 times 5. 2 times 2 times 3 times 5. It doesn't really matter because multiplication can be done in any order, but I just think it looks a little neater, a little bit easier to read if we put them with the numbers in ascending order like this. It also means that when we want to collect those like terms like 2 times 2 and show that as 2 squared like this, that we can see that because they're together it's easy to collect them up. A little bit harder if they're all spread out, particularly if you have quite a long list. So 2 squared times 3 times 5 is our answer for this one. Okay, I'm going to let you have a go at a few questions now. I'd like you to make factor trees for each of these numbers. Pause the video here while you work it out, and then when you're ready, press play again and you can check your answers and see how you got on. Don't forget when you get to the end of your tree to write down the answer in a line, so 2 times 2 times 3, for example. Okay, pause the video there. Welcome back, guys. Here are the answers. I'm sure you're desperate to know if you got it right. Okay, so 21 is 3 times 7. That was a nice easy one to get you started. It just has a single pair of factors. The first pair that you can think of are actually prime numbers. 18 is made of 2 times 3 times 3, or we can write that as 2 times 3 squared. 24 is made up of 2 times 2 times 2 times 3, or 2 cubed multiplied by 3, if we collect those like terms there. 56 is made up of 2 times 2 times 2 times 7, or 2 cubed times 7. 72 is 2 times 2 times 2 times 3 times 3. Easier to write that as 2 cubed times 3 squared. And 120, 2 times 2 times 2 times 3 times 5, or 2 cubed times 3 times 5. Well done, I hope you got those right. Go over now and have a little practice on the interactive activity. The link for that is on the school website. Good luck with it, guys. See you next time. Bye.